Audience, you are even on time before the coffee break ends, and everyone is here. So let's get started because we are all around. So now we will continue the discussion or get all the answers. So next speaker is Petrov, dust in the near environment of classical T Tauri stars.
Thank you. Let me start with things maybe well known to you, and then I will proceed with more recent results. Classical T Tauri stars are lower mass counterpart of the Herbig AE stars. The main difference from the Herbig stars is that T Tauri stars have convective shells, and as a consequence, strong magnetic fields generated by the dynamo mechanism. Another difference is lower temperature of T Tauri stars. Due to lower temperature, the dust sublimation distance shifts closer to the star at about 0.1 astronomical union. The dust comes just in the inner rim of accretion disk. Therefore, the dust may be involved in the magneto-hydrodynamical processes caused by interaction of the magnetic field with accretion disk. And this is also reflected in the variability we observe. I will review briefly these three topics related to the role of dust in the observed variability of T Tauri stars, dippers, dimming events, and the dusty disk winds. First of all, the presence of dust around T Tauri stars are well seen in polarized light. This is a rather large-scale structure, of about 500 astronomical union. The dust in the near environment of a star within a fraction of astronomical union reveals itself in variability of the second stellar extinction. Therefore, the main tools remain to be photometry and polarimetry. The main questions we try to answer are: where is obscuring dust? Why does it appear on the line of sight? And what is the dust properties, for example, gas-to-dust ratio in the obscuring matter? The most representative sample of light curves of classical T Tauri stars was collected during coordinated observations with two space missions, Korot and Spitzer, Korot in visible and Spitzer in infrared. Great number of classical T Tauri stars was observed during 1 month. And this program revealed, or it's better to say confirmed, the multiple origin of light variability, including periodic due to cold spots, then short events of accretion, which are called busters, and stochastic variation due to circumstellar dust, or discrete fading events lasting shortly, also due to dust obscuration. And the last category, dippers, are largest one, about 20% show this effect. This is just an example of the dippers. The best studied example of a dipper is, of course, AA Tauri. It was an intensive program initiated by Jérôme Bouvier and his team in the beginning of, or at the end of 90s. As a result of this program, they elaborated a model of this type of variability. AA Tauri itself is a typical T Tauri star, nothing special, but high inclination. The star is seen H-on. Stellar brightness and emission lines, Balmer line profiles, vary with a period of stellar rotation of about 8 days. Polarization rises as the star fades, and the second stellar extinction corresponds to the interstellar law, that is, the dust particles are small. Remarkable is that the shape of the minimum is changing in different epochs of observations, and that needed to be explained. The model suggested by the Bouvier team is the warped disk model. If the stellar magnetosphere is tilted, then the inner disk is warped, and this disk warp periodically eclipses the central star, causing a modulation of its optical light curve. Another good example of the Dipper is Calcium-15, which was observed with Keller K2 mission during almost 2 months. Many dips were covered, and almost each minimum has different shape. According to the disk warp model, the inner disk warp is changing due to temporal variation in the magnetospheric topology. Magnetosphere itself is changing. So on a time scale of several rotations, it changed the warp itself. Another example of a Dipper is this one. It's a particular one because a low gas-to-dust ratio in the inner disk was detected. The authors suggested that excess of dust in the inner disk may be a result of the disk evolution towards the dust-dominating disk, or fragmentation of large bodies, that is collision of planetesimals, which supply more dust in the inner disk. The dimming events in Tauri stars is another type of variability caused by the dust. It may be characterized as sudden increase of circumstellar dust extinction on the line of sight without concomitant change in the accretion rate. It's formulation by Bouvier. Not many T Tauri stars are known to show this effect, maybe a dozen or so. And we see AA Tauri again in this list. This has been known as a Dipper, but starting from 2011, it was faded and still remains faint up to now. Another well-known, well-studied dimming star is RW Auriga. It's well-studied just because it's bright enough. It also shows a dimming event at about 2011, and then it was repeated several times, and up to now the star shows this kind of variability. The amplitude is quite large. There is no any periodicity in the repeating of these dimming events. Each one may last for about 1 year or so. In one of the dimming events, in 2015, we discovered, well, Chenaurin discovered new effect. When the star gets faint, invisible, it gets faint also in G, H, K bands, but it got brighter in L and M bands. It means appearing of hot dust. And we suggested that this hot dust is the same material which obscures the star. The questions are where it comes from. Is it hot dust in the disk wind? Is it hot dust which comes from the disk due to some inner disk perturbations? Or is it destruction of planetesimal, as was suggested earlier? Distribution of energy, it must be somewhere here, or it lost. The distribution of energy shows that the temperature of this hot dust is about 1,000 kelvins. In another dimming event of the same star, gray extinction was discovered. That is, large-size particles appeared on the line of sight. Another very mysterious effect is that the photospheric absorption lines were veiled during the dimming event. It was several dimming events, and in each of these dimming events, the photospheric line depths were reduced. The line depths were reduced, but the line width remained the same. This veiling effect is usually attributed to continuum radiation from hotspots on stellar surface. So the question is, how can it be correlated with the obscuring dust? This is the hotspot on the surface of the star, and dust is just farther away. During the dimming, we don't see the star itself. We see only scattered light, the light scattered by dust particles somewhere above the disk plane. So in order to explain this veiling effect, we should assume that the dust particles are somewhere close to the hotspot, maybe even in the accretion stream, if only the dust can survive in the accretion stream. Otherwise, it would be difficult to understand this strange effect. And no major accretion variations were observed across the dimming events, not only here, but also in other stars. So the dimming events has nothing to do probably with any drastic change in the accretion rate. Another important result is a high level of polarization during the minimum brightness. Polarization degree in I band reached up to 30%. And the conclusion made by Dodin and his group is that polarization of RWA during the dimming was generated by scattering in a dusty wind which flows along the rotational axis, because the polarization angle coincides with the jet axis. Maybe it tells something to us about the mechanism of these dimmings. Another interesting result was obtained by Chandra X-ray. They observed RW Riga during one of the dimming in 2017 and revealed that iron abundance in coronal gas was an order of magnitude above solar, in contrast with previous subsolar measurements. They speculate that breakup of terrestrial planets or large planetesimal might supply a gray extinction seen in the optical and also provide high metallicity in the coronal gas. Alternative scenario was suggested in very recent publication by Garate. If I understood it correctly, numerical simulation of accretion disk evolution shows that the dust particles may be accumulated in the dead zones of low turbulent viscosity. And when such a dead zone is reactivated again, the accumulated dust is accreted onto the star. Maybe it's more physical than previous speculation about the crash of planets. Oh, this story was told yesterday, so I skip it. Then dust in the disk wind. The best example of an Uxor among classical Tauri stars are RY Tauri. The star is permanently obscured by dust, so we don't see the upper part of this diagram, only the lower part with the bluing effect. The star is intermediate mass. In between T Tauri and Herbig AE, the star is seen at a high inclination. So why this star is remarkable? In this star we observed a strange effect. H-alpha line profile correlates with stellar brightness. We know that for this star, brightness varies solely due to dust extinction, not due to variable accretion. So how to understand this correlation? The P Cygni profile, which shows enhanced outflow of wind, more often observed when the star is bright. So if we measure the ratio of blue to red fluxes in H-alpha, it well correlates with stellar brightness. So we suggest that probably there is an impact of wind on circumstellar dust. The physics of this is not clear. We may only speculate that dust particles are coupled to the gas flows along the magnetic fields in the disk wind, and magnetospheric ejection may disturb the magnetic field of the disk and thus change the flow of this dusty wind. The typical time scale of these variations is 2 days, and the typical velocity in the radial velocity in the wind is 100. It gives us a typical distance, 0.1 astronomical union, which just coincides with the size of the inner disk. So there may be a close relation between the magnetospheric ejections and the dusty disk wind. The dust temperature, as it comes from the spectral energy distribution, is 1500 K. There is another star, ICU Auriga, with stellar parameters very similar to RY Tauri, where the dusty disk wind model was built using much more advanced methods, near-infrared interferometry and the radiative transfer model. So interferometry gives us image of this dusty environment of the star. We see the dust radiation in the distribution of energy. And the radiative transfer model showed that there is a flared disk with inner radius of 0.18 astronomical union. The grain size 0.5 micron. It is a silicates with this temperature. And the dusty disk wind is a necessary component of the model. Only the dusty disk wind may successfully account for the K-band excess. It's here. Without the dusty wind, we would not observe this excess. So it comes just to a simple conclusion that Uxor effect is common for Herbig AE stars and T-Tauri stars. A dusty disk wind is a source of second-star extinction in classical T-Tauri stars. The outflow events may affect the near-dusty environment. And a deep, long-lasting dimming occurred due to inner disk perturbation or collision of planetesimals. Thank you.
Questions?
I have a question regarding this RW Auriga, right? You mentioned this paper,
Garate.
Yeah, that the dead zone, activation and accretion. As I understand, there is a dead zone where dust particles accumulate, and then there's a dead zone where there's heat ups and MRI, for instance, activated, and the entire thing is accreted. Then it can explain dusty wind, right? The excess dust would be
they say...
But we don't see. So you mentioned that these objects, they don't see significant changes in accretion. So if we consider this mechanism working, then there's this inconsistency between unexpected accretion burst, which would be produced in this case.
Yeah, I understand the question. As I understood them, they say about accretion of dust accumulated. But you know, the mass of dust relative to the mass of gas is very small. It's 1%. So it means nothing in the accretion. It cannot add something to accretion rates because the dust is...
But gas is also driven. So that's the problem. It's not only
there is no accumulated gas, there is only dust is accumulated. There is only dust is accumulated.
No.
There is only dust is accumulated. That is, the gas to dust ratio is different, nothing.
I model these effects, I know. So dust indeed is accumulated. But when the MRI is ignited, the entire thing is driven on the start. Gas and dust. So there must be a burst.
Okay.
I will show tomorrow an animation of this effect. It must be a burst.
I'm not advocate of that paper. I just read it 2 days ago.
Yeah, but you mentioned that the Uxor phenomenon also takes place in classical Tory stars. I don't mean these intermediate stars, but the normal classical ones, like A tau type dippers. Do they show bluing?
Yeah, yes. The dippers are, yes.
They show bluing.
This phenomenon is observed in many T-tower stars, yes. Not only in the intermediate.
Okay, because is the Uxor phenomenon, I just wanted to be sure that was clear. It's not just a dip, right? It's not just that it goes down in magnitude. The specifics of an Uxor phenomenon is the bluing effect, right?
Oh, I don't remember if there are bluing effect during the dippers. Probably yes, but polarization rises.
AA tau.
In AA tower, yes. There is bluing effect. Yes. Okay.
So it is the same one.
Yes, I say yes.
So you again about RWRD. So you mentioned this calculation about planet-thermal collision. With this scenario, is it possible to do follow-up observation of such dust clouds? Because such dust clouds created by impact event can evolve quite fast in several years, as I heard from those people who are doing extreme degree disks. So the dust will spread out and it becomes more optically thin, and it will also be ground into smaller grains with collection state. So can this be tracked with follow-up observations?
I'm afraid that
Yeah. Can you?
is it a comment or question? Just
A question.
question.
A question.
I want to ask you one question.
Sorry, I want to ask about the possibility of doing follow-up observations to study the evolution of such dust clouds. Is it possible? Do you think it's fast enough to be followed in years?
Must be followed, of course. The leading event is continuous. Many people are following this.
Okay, sorry.
Sorry.
Yes, please.
Could you tell anything about the dust size, maximum dust size?
That's particles.
Particles from the multi-wavelength observations. I suppose that absorption, efficient absorption depends on the dust size, and because you do different wavelength observations, you can do some.
Well, in some stars, large dust particles were recorded because the extinction was gray. For example, in one of the dimming events of RW Riga, the extinction was gray, so the size of particles were large. But in another star, SU Riga, The size particles are 0.4 microns, it's normal. So it's a variety.
There is no grown dust, right?
Oh.
Do you see any evidence for grown dust there? I mean, if grown dust absorbs a maximum absorption for larger particles, shifts to longer wavelengths.
Oh, I don't know these details.
So just doing this observation at different wavelengths, we in principle can infer dust sizes.
Well, it's interesting questions, but I don't remember I ever heard this in literature.
Just a comment on that,
Yeah.
and then I had a question.
Yeah.
On RW Riga, using 2x shooter spectra, so we had the whole ACD, and trying to model the optical depth dependence on wavelength that we derived, we needed large grains up to a few hundred microns. We couldn't do it with small grains. But of course, as you know, there is always a great area of ambiguity because we don't really know the chemical composition of the grains and a lot of other properties, so you can always just say, this is my idea about grain, and with this idea, silicates of a certain kind, for example, then I get this result. I mean, it's never, that is a comment.
Sub-millimeter dust grains, right?
Yeah, not millimeter, but a few hundred microns. So that was with a certain kind of
Probably
silicate.
it's difficult to derive along larger dust grains. Or
It becomes gray then.
Huh?
Well, that was derived from the blue to the near infrared, and if it was much larger than that, then it becomes gray. It was not gray. It was not gray. So that's all I can say. So, but
And I think
the exact numbers.
We had yesterday the partial blocking of the star, and it fakes the extinction law. So
That is still another story, of
So-
course. Yes. And all the stuff. Can I ask my question? Sorry.
If you have extinction only from optical to near infrared, then you cannot say it have to be several hundred micron. Like 10 micron grains is also derived from optical.
Well, no, sorry. What I said is that the maximum size. So I always assume that there is a distribution of sizes with the usual power law, and then you can constrain. You cannot constrain the minimum size. It has to be small. But then you can constrain the maximum size. But it depends on the number of assumptions. But I am saying that small grains that did not fit. Okay, so that how large I wouldn't. I had a question on the other hand, which is about the dusty winds. They have to be variable. Have you any idea of what can cause the variability, and if we can observe the cause of the variability? You know, there was something about that, about the mass accretion rate. Is there any way that we can do that? And related to that is, how much does the mass loss rate have to change to give us this episode of extinction? Factor 10? Factor 100?
Well, the mass loss rate is not much changed, I would say. But where the first part, where the dust comes from.
If you can check it. Well, you need a variable wind.
Yeah.
No? Because if everything is static, we don't see these episodes.
What we measure is extinction, nothing
Yeah.
else. We measure only
You
extinction.
need to have a variable wind.
Yes.
Now, winds are driven by radiation or by by accretion, usually. No? Either it's a photoevaporative wind or it is related to the accretion. I don't know any other wind in classical simple models.
I think this is a disk wind, and the disk wind carry the dust particles from the disk plane. It's just
This
carried.
wind is driven by accretion rate.
Centrifugally accelerated disk wind.
Yes, but you need to change something. So what I
We need to change the
wondering
dust.
If there is anything that we can test that is actually changing.
The dust is the gas to dust ratio is changing, and the mass loss rate also changing. Why there is different amount of dust in the wind? That is a question.
Yeah.
There must be non-uniform distribution of dust within the accretion disk, and when the accretion disk matter comes closer to the inner disk border where the dust is carried away. Then if the dust is somewhere accumulated, it finally must be thrown to the wind.
You are thinking that what changes is not the mass loss rate, but the amount of dust that you have?
I think both. Why not? Both are changing, both parameters.
And can we check if there is a change in the mass loss rate?
We can check the dust-to-gas ratio from observational techniques. It's possible. Gas-to-dust ratio
From
can be...
observations also?
Hmm?
I missed from observations?
From observational data, we can measure gas-to-dust ratio.
How?
Oh, how? You have to measure the strength of resonance lines, doublets, for example, to measure the variability in the gas density. And the dust density is just a measure of circumstellar extinction. So this can be measured.
Okay, we move on. Let's thank Peter again.